Your password can be changed, your credit card can be canceled, but your fingerprint, your face, your voice, those are yours forever. And here's the scary part. If your biometrics ever get hacked, they don't expire, they don't regenerate. It's a lifelong risk. So how could we possibly trust biometrics to secure our bank accounts and our finances? This is the question I left you with in the last video. What could we possibly do to protect our biometric information? And the answer is biometric encryption. What this does is it takes your biometrics and puts it into mathematical data that's either impossible or very hard to decrypt. And we're going to get into those methods shortly. Okay, so our first biometric encryption method is cancelable encryption. And so we're going to get into this very slowly. So the formula for this is ciphertext is equal to template times matrix. So your ciphertext is your output, your template is your biometric template that you're trying to encrypt, and your matrix, we'll get to that in just a second. So we're going to take the example that your template is 1, 2, 3, 4, and that your matrix is this. So your matrix would be the same length as your template. So in this example, my template has 4 numbers, thus my matrix is 4 by 4. But let's say in a regular example, like how I'm about to show my project, in my project we take 128 numbers of your biometric template. So my matrix would be 128 by 128. And essentially what a matrix is it's a long vector of numbers organized in independent rows, as you can see on the screen. And so if we were to carry out this formula, so your template times your matrix, you can see that over here, our entire template is being multiplied by each row and through each operation. So, and then at the right over here, we get our new template, our new ciphertext. So essentially what this does is if someone were to hack and potentially get the ciphertext, they wouldn't have a matrix, thus they wouldn't be able to calculate what the actual template is. And let's say someone were to get a hold of the ciphertext, we could always change the matrix and recrypt the template, which is the benefit of cancelable encryption. And so this is obviously a small scale example, but in a real example, like I mentioned before, where usually we do take 128 numbers, the matrix and the template would both be a lot bigger, and the matrix would be a lot more complicated. As opposed to all of it being the same number, the matrix would have a bunch of different numbers, and they'd all be Gaussian numbers. Gaussian numbers are randomized numbers, but with a uniformed randomization, which means they're all around a specific median. And so when we're talking about biometrics, all these numbers should be close or somewhat near to 0, between -1 and not past 1. The next biometric encryption is quantized hash. So essentially, this is a quantized version of biometric encryptions to outbeat quantum computers. And what we're doing here is we have a threshold whether to take a biometric template and put it into binary numbers, which is 0 and 1s. So for example, our template here is listed on the screen, and our threshold is 0.01. So if a number on the template is below that, it'll be, or sorry, if it's above it, it'll be 1, and if it's below, it'll be 0. So we can see the output on the screen. The first number is 0.445, which is greater than threshold, thus it's number 1. Our second number is negative 0.44. This is less than threshold, thus it's 0. So that's essentially how it works. In actual code, what we do is we take the template, we get the median of all the numbers, and that would be our threshold, because that makes it a lot more accurate and it has some uniform to it. The third encryption method is AES, the Advanced Encryption Standard. And so essentially what we're doing here is there are 2 parts to this algorithm. So in this example, we're trying to encrypt the message 100. And what we do is in order to encrypt that, we use a key to encrypt this. So we're going to focus on the left side. For the example, our key is number 2. And the algorithm, we're going to choose a very simple algorithm. So the key times the message. And then your output would obviously be 200, 100 times 2. So the problem, what we have here on the left side, is that every time if a user were to verify their face, let's say through a Face ID simulator, their output would always be 200 because let's say 100 is their biometric template. Every time they go to verify, 100 would go through this algorithm and the output would always be 200 because the key always stays the same. Here's an issue. If someone were to look at this, they would notice a pattern because the output would always be 200. It's not safe. With this pattern, they could determine both your biometric template and they could determine the key. So the second part to AES is the IV key, or the initialization vector key. And what this does is it adds a new piece to the algorithm. So our message will stay the same, 100. Our key will also stay the same as 2. But the IV key, each time a user passes information, the IV key will be random each time. And so again, we're using a simple algorithm, IV plus the key times the message. And then your encryption will be different every time because your IV key is randomized every time. For example, let's say I'm using a Face ID simulator and I'm gonna show my initial face. So it's gonna use this template to compare my face every time. So my template would be 100, my key would be 2, and the randomized key for this time would be 3, for example. So it would be your IV of 3 plus your key of 2, which is 5, times your message, which would be 500. Now, let's say I'm using this again, and this time, my face is the same, so I'm passing 100. The key is the same, so I'm passing 2. But because I'm using it a different time, the IV key will generate a random key each time. So let's say this time, instead of 3, it could be 6. So over here at the bottom, it would be the IV key of 6 plus the key of 2, which would be 8 times the message, which would be 800. So this way, with the IV key in AES, it's not going to constantly provide the same output because that can give away the AES key, which is very valuable. Because the IV, it's going to randomize the output each time. So let's say if someone were to have access to all these outputs, they wouldn't be able to put pieces of information together because there would be no consistency to the outputs. This is the fourth encryption method, but really it's a continuation of the last one. As I mentioned before, the AES key is very valuable. So what this does is it's a double layer of AES. This time we're going to protect the AES key itself. So in this example, the key is 2. So the goal of this method is to protect that number 2. So we're going to ignore the bottom and we're going to focus on the bullet points for now. First, we need to create a wrapped key. So in order to do that, you're going to choose a password. And for this example, we can choose hello. Then we're going to generate salt. So that would be just random 16 numbers or bytes. And what the algorithm is going to do, it's going to take the password, it's going to take the salt, and it's going to create a wrapped key, which will be the same length as the AES key. And so now we're going to take both the original AES key and the wrapped key, and we're going to put it through AES again. So we're going to follow the same format as last time. So right now we're trying to protect the key. So for this time, we're going to pass it through AES again, and the message won't be my biometric template. It's going to be the AES key I used to encrypt my biometric template. Then the AES key for this wrapped key would be the wrapped key we used from the password and the salt. Then, as you know, the IV key is random each time. The algorithm would be the normal AES algorithm. Then the encrypted output would be your protected AES key. So if you look at it from a bigger standard, first we're going to encrypt the template. Then the key we use to encrypt the template, we're going to encrypt that again through AES. And that's the goal of both of these encryption methods. Okay, so the fifth algorithm is SHA-3, and that stands for Standard Hashing Algorithm. It's a modern day hashing algorithm. It's supposed to be futuristic in a way. However, it is a one-way algorithm, so it cannot be decrypted to be reversed. So the way you would verify someone, so let's say, once again, you're in a Face ID simulator and you're trying to verify yourself. Instead of the algorithm decrypting the original one, it would pass your current biometric template through this algorithm, and it'll compare the encrypted original with the encrypted verify to see if they're the same, are they similar, are they very different, and that's how it would verify or deny you. So how this algorithm works is it consists of two parts, the rate and the capacity. The rate is the information or data you're passing through, so in this case, the biometric template. The capacity is a constant set of numbers, and what it does is in the round one, it'll encrypt the rate with the capacity, so the numbers will be infused into the rate. Then before it moves on to round two, the rate 1 data will be XOR'd. Then we're going to do it again. Then round two, the rate will be encrypted with the capacity again. Then before moving on to round three, the rate will be XOR'd, and then it'll keep repeating this process as many times. It can be repeated hundreds of times, thousands of times, no matter how you want it, because either way, because the capacity is the same set of numbers and because it's using the same algorithm, it won't change. If you're passing the same data through, it won't change the second time because it's always following a consistent algorithm. The only reason this algorithm is considered irreversible is because the capacity. My computer or my program might use a certain capacity, but another program might use a different capacity. And if you were to have 10,000 quantum computers calculating these different possibilities for the capacity, it would take them trillions of years just to find each and every one, which makes this algorithm so strong in a sense. The sixth verification method is fuzzy commitment. And so what we're doing here, the reason it's called fuzzy commitment is because biometric templates change each time, right? If my circumstances can be different, my hair might have changed, the lighting might be different every time I'm going through a Face ID. So the biometric template won't always be consistent. So fuzzy commitment uses something called ECC, error correction code. And what it does is basically when you're passing your biometric data through, the ECC will adjust it so that it'll get rid of all these irregular differences. So those lighting mishaps that might change the biometric template a little bit, the ECC will be able to get rid of that to make it just exactly as the same as the original one. So let's focus on the example at the top. So the biometric example here is 1010, and then what this algorithm does is it generates a random key. In this case, it's 1000. Then the algorithm is very simple. It's just going to XOR the biometric by the key, and then you get your output, 0010 in this case. And then to verify, you're going to take your new biometric. So let's say I'm going again, I want to verify myself. And once again, it's the same biometric template. My face hasn't changed. It's 1010. Then I'm going to take the output of my previous Face ID encryption, which is 0010. Then we're going to XOR the new biometric by the fuzzy commit to get my key. Now, this key output, if it's the same as the original key, then the program will know it's the same person. If it's different, then it's going to know it's a different person. And so when storing information, the algorithm will only store the fuzzy commit and it'll store a hash key. So it'll store the key, but it'll store an encrypted version of the key. So that way it's more secure. And the last encryption method is homomorphic. And what this does is I'll run you through a quick example because that'll be much easier to understand. So what it does is you have your original template on the screen. Then it's going to generate a random key. And the template and the key must be the same length. Then M stands for modules. And this can be any number, really, but it's much easier if you have a number that's divisible by 10 per se. So in this case, it's a million, because this M is just being used to scale a number, and you'll see how we do that. So step 1 is to scale a number. So we're going to multiply our template by our variable M. So as you can see, each number in the template is multiplied by M. So 1.234 becomes 1,234,000, and yeah, so forth. And that's done for each number in the template. The second step is you're going to take your results from step 1 and you're just going to add the key values to it. So 1,234,000 plus 42, which is the first number of the key. And you do that for each number. And then the last step is you're going to take your output from step 2 and you're going to divide it. You're going to take the percentage of that number. So we're going to take the percentage of that number from M. So the percentage of 1,234,042, the percentage of that to a millionth would be 34,042. And that's what we're doing. If you want to see a normal example, if you look at the step 2 output, basically the first 2 numbers are being removed, and then the rest is being put as the output for step 3. For example, in the second one, the number is 2,345,073, and then we're just removing that 2,3 at the beginning, and then that's the output for the encrypted numbers. And so that's how this encryption method works. And when we want to verify a biometric template through this verification or through this encryption method, what we do is we use the same key, we use the same M value, and we're just passing that data through this algorithm. Then we looked at the encrypted versions to see how similar are they the same, are they different, and then we use that to defer whether they're different or the same to each other. So that about sums up our encryption methods. Okay, so we talked a little bit about how these encryption methods work. Now, this is my project, and essentially what it does is it takes a mock biometric template, and it's going to use each of those encryption methods that we talked about on that mock template. So that way you can see how it looks in play. And so over here, essentially it's not going to show you step by step, it's only going to show you the outputs. But after this, we're going to deep dive into the code a little bit, that we can see how it's coded and how that biometric encryption actually works. So over here, we're going to generate our mock template, and that's our 128 numbers. Then we're going to do cancelable encryption, then quantized encryption, then the AES encrypt. Now, over here, for the wrapped key one, if you remember, we have to pass a passphrase or a password into it. So let's keep it simple, hello, and then wrap key. So what it did is it took my password and it made a wrapped key using that password and some salt. And remember that salt over here is just a randomized 16 bytes of numbers. And so the next encryption method is SHA-3. and that's the result from there. Then fuzzy commit, as you can see, fuzzy commit focus on those zeros and ones, so you can see how it's displaying each one of those numbers. And then the last one is homomorphic. Once again, you can see that output right there. So now we're going to deep dive into code to see how that works. Okay, so this is our code, and in all honesty, it is pretty long. It is 340 lines, and that can be overwhelming, but we'll get through it one by one. So obviously, as you know, I explained previously, we don't need to focus on the index and style. They're just to actually put all the pieces together on the screen so it looks nice. So we're going to focus on the actual code. So this first block of code are just helper lines. So that way we don't have to keep coding those little tedious parts, which are really long, but they don't have any significance. So we're using helper codes to shorten it up. That way it's not too hard to code, not too long either. Over here, we're basically taking everything on the index and we're putting them into variables. That way we can display the information on the screen. Also not too important. Now over here, we're going to get into the real stuff. The first part is to generate the mock template. So over here, this is where we actually generate the template. You'll see a lot of this times OFFF, and that's to actually determine the length of these numbers. And you'll see a lot of these the S variable. If you want in the code, you can pass a seed if you want to, but that makes it a little more complicated. So I just like to press the generate random number. And over here, this is for the actual button to actually generate the mock template, and it'll call the function above. Now we're going to move on to the first encryption method, which is Cancellable encryption. So what this code does is it's going to generate a very long vector of numbers. And then we're going to use that vector of numbers for later. So this generates that vector of numbers. Then essentially what this piece of code does is it's going to take that vector of numbers and it's going to make it into the matrix. So our biometric template is 128 numbers. So that vector of numbers, we're going to split it up into 128 by 128 matrix. Then over here, we're going to do the actual calculations. We're going to multiply our biometric template by the matrix. Then once again, this is just for the button. So when we click it, it'll call these functions. And over here, there's also a download button there. If you want to download the output, that's also an option too. The next part is the quant size button. And over here, it's very simple. What we're doing is we're going to take our biometric template and we're going to get the median of all those numbers, and that will be the threshold for our binary numbers. So if any number on it is greater than the threshold, it's 1, and if it's below the threshold, it's 0. And that's what we're doing. It's a very simple piece of code. And over here, once again, that's also just for the button. Now we're getting into AES. And so what this piece of code does is it generates a raw key, and over here we're going to turn that key into a proper format. So we're not actually coding AES on our own. We're using something called web crypto, and that has an AES engine. So we're just going to generate our pieces of information, pass it through that engine, and it'll do all the calculations for us. So in this line, we generate our key and turn it into the proper format. In this line, we're generating our IV number. Remember, it's random at all times. You can see the random values over here. Then we're putting our IV and our text encoder into a proper format so it can go through the engine. Then over here, we're passing our biometric template, our key, and our IV into the web crypto engine. So that way it'll do the AES calculations for us. And so that is also just once again for the button. Now we're going to go below. Now Wrapping the key is a lot more complicated. So once again, over here, we're gonna take that password. So for example, I said hello. We're gonna take that password and we're gonna put it into a key. We're gonna make that password a key. So it has an algorithm to take hello into a key. Then what it's gonna do in this line is it takes that password. It takes the salt, which is just random numbers. It's gonna stretch that into a wrapped key. Then over here, we're gonna take our AES and we're going to turn it into a proper crypto format once again. And so this way we get our full proper formatted wrapped key. Now over here in this line of code, we're taking our wrapped key and our original AES key and we're again passing it through AES to get that further encrypted part. Now over here, it basically undoes this if you ever want to unwrap the key for later. That's obviously a different part we can talk about. Then this once again is for the button. Now SHA-3 also the exact same thing. Very complicated, but we are also using web crypto for this, has its own engine for this. And so essentially what we're doing here is we're passing our biometric template and we're converting it into a string so that it's compatible with the engine, and then we're passing it through the SHA-3 256 engine. 256, the number after SHA-3 is just the bits. So I believe there's 256, there's 540, and 1080. And so over here for simple fuzzy commit, what we're doing is we're stretching our biometric templates by 3. So let's say our mock template was 011. Because we're breaking each bit and timesing by 3, it would be 000, 111, 111. So each number in the template will be multiplied by 3. So that way, if there's any small changes, like any noise, for example, if I'm going to go verify my face and there's lighting changes behind me, it'll be able to get rid of that because the numbers are so detailed and stretched. And so then we're doing a very simple version. We're just taking that helper code and we're going to XOR it by the helper code. Usually we generate a random key as we discussed before and we'd XOR it by that. Then this once again is also for the button. Now homomorphic. So over here, we're defining that M value. Then over here, we're generating that random key. Then this is where we do the actual calculations. Over here, this first part is where we scale it with the M variable. Then we add the key onto it. Then we find the percentage of it. So we reduce it back by M right over here. By M again. And so that's the full calculation. So we're going to do that for every number in the template. And then we're going to return the normal values. So this other line that you see, this is another display method. Over here, we're shifting the key by 7 just so that you could see how homomorphic actually uses a key. Because it's just addition. So if we're shifting by 7, that means in the other values, they'll all be subtracted by 7. So that's the truth behind biometric encryption. It's not science fiction, it's not theory, it's just math and cryptography. And it can be overwhelming sometimes, but once you really delve into the understanding and the basics of each, you get a good understanding of how each encryption method works. And notice something, we did not, at no point did we ever store the original fingerprint or Face ID. We never stored the original template, we always stored the encrypted version. And let's say we're storing a key or two, something that helped us encrypt that data. We don't store that raw data, we always encrypt those keys as well. That way it's always double protected. And the importance behind biometric encryption is that if there's ever an incident where the encrypted data is hacked, they would not know what to do with it because it's impossible to decrypt. And that's the significance of it. So thank you for watching.